if you had to guess what molecular geometry means, tell me, what do you think? Without like, give me a simpler definition than this. The shape of a molecule. That's right. Geometry, we deal with shapes, right? So we're talking about molecular geometry. We're looking at the shape of a molecule. So everything we've done so far has been two-dimensional, right? It's just laying on flat on a paper. What we're going to start looking at now is how we can imagine that molecule in 3 dimensions, right? We're going to kind of bring it to life and see how it's going to rotate, how it's going to form, what shapes is it actually going to take on, okay? So that's the goal. In order to do that, we look at the number and type of what's called an electron domain to determine the molecular geometry, okay? So you might be asking the question, there we go, what's an electron domain, right? So I said you got to use electron domains, but you should be asking the question now, well, what's an electron domain? An electron domain is essentially, and I'm going to change this definition here. Yeah, I guess that's fine. How many things surround to the central atom? How many things surround the central atom? Okay, so an electron domain is how many things or what types of things are around the central atom. So now, if I'm looking at a central atom, I'm going to pick a different one. You don't have to draw this. I just want you to look for just a second. How many things are surrounding the central atom? We've got a bond, a lone pair, a bond, and a bond. So I've got 4 domains in this structure. Okay, around the central atom, I have 4 different things. A bond, a lone pair, and another bond. Okay, does that kind of make sense? I'm going to go over these a little bit more specifically, but when I say the things surrounding the central atom, that means they could contain either a bond or a lone pair. Okay? So, when we start trying to assign a molecule's molecular geometry, we're going to use a theory, okay? Do you have what we need off this slide? Okay. We're going to use this theory I call it VSEPR theory. I know that's not really the acronym it gives, but that's just how I call it, okay? VSEPR theory stands for valence shell electron pair repulsion theory. So I'm going to give you a second to write that down, and then I'm going to break it into its parts, okay? This is an acronym that I think you should know. So highlight this in your notes or whatever, but it could be that on the quiz or test, I ask you, what does VSEPR theory stand for? And over the years, I've gotten quite the responses that are not correct. So just maybe take a note of what this means, okay? Valence shell electron pair repulsion. Okay, otherwise you're going to make it up, and I've seen lots of those, okay? So this is what valence shell electron pair repulsion, VSEPR theory, means. The electrons that participate in bonds are in what? Where are they in an atom? They are in the valence shell, right? The electrons that participate in a bond have to be the outermost electrons, right? So the only electrons that bond are valence electrons. So it means we're looking at the outer shell electrons, electron pair. Electron pairs exist either in a bond or in a lone pair, right? So electrons only exist in pairs, okay? So that means we're looking at the outer shell paired electrons. Could be in a bond or could be in a lone pair. And then what does repulsion mean? They want to push away. They want to repel one another. So let's talk about this. If I've got electrons in a bond and electrons in a lone pair, what charges do those electrons have? Or what, if they're just electrons, what charge do they have? They have a negative charge, negative charge. Do negative charges want to be right next to each other? No, they don't. So that means within a molecule, you don't have to write down this whole definition if you don't want to, but all it says is that within a molecule, these valence electrons repel each other. Okay, so repulsion between the sets of valence electrons surrounding an atom causes these sets to be oriented as far apart as possible. Okay, so the electrons within the bonds and within the lone pairs make those atoms spread out. Okay, they make themselves situated, and so they're as far apart as they can possibly be. And there's a few configurations that are consistent. Okay, so the basic definition is electrons repel each other. They want to be as far apart as possible. So that is why if I'm drawing a molecule like BeF2. Let's say I'm drawing a molecule that looks like that. When I draw my skeleton, I'm not putting them here. I'm sorry, not Fe. I'm not putting them here and here, right? Because if I were going to bond these, are those bonds as far apart as they could possibly be? No, that's not how that molecule would be oriented in 3 dimensions, right? Those two F molecules are not going to sit right next to each other. They want to spread out. And so the fluorines would be as far away as possible so that these two bonds have as much space between them as they can. So these electrons want to be as far away as possible from one another. So if there was 3 things, like how many degrees away are these from each other? 180 degrees apart. Okay? If there were 3 things that were bonded, what would be the maximum space in terms of degrees that they could be from each other? 120, right? They could be 120 degrees from each other, right? Does that kind of make sense? 3 things have to be 120 because the whole circle is 360 degrees. Okay? All right, we're going to get to that degree part here in just a little bit. But all right, so do we understand the whole theory of VSEPR theory? It just is basically saying electrons repel each other and they want to be spread out. That dictates the shape of the molecule. Okay? Those electron repulsions completely dictate the shape of the molecule and how it's going to look in 3 dimensions. Okay, so now we're going to talk about, well, what is an electron domain? We said the things surrounding an atom, okay? But I'm going to go a little bit more specific. Domains can be considered either bonding domains or non-bonding domains, okay? A bonding domain contains at least 1 bond. And I'm going to not just say a bond, but it contains at least 1 bond. Okay, at least 1 bond. That means that a double bond is still only considered 1 domain. Okay, so a double bond is still 1 domain. That would be the same for triple bond as well. A triple bond is still a single domain because it's taking us to 1 thing. The second type of domain is a non-bonding domain. So what do you think a non-bonding domain has to contain? It contains a lone pair, right? Because those electrons are not involved in bonding. And so if they're not involved in bonding, they have to be a lone pair. Okay? So they're either bonding domains or non-bonding domains. We're going to look at how we identify the difference and all that kind of stuff here in just a second. Something that maybe I should tell you one more time is that when we're counting domains, we are only looking at the central atom. Right? The lone pairs around outer atoms don't affect the shape of the molecule. The things that affect the shape of the molecule are the bonds and the lone pairs around the central atom, because that spreads it out, right? Think of the central atom as the origin of your coordinate system, right? You've got 360 degrees around it. Those electrons are going to spread out around that origin. Okay? Are we good on that part so far? If you want to draw it out on your notes, that's fine too. But we're going to look at this water molecule. This is drawn in the correct shape and in the correct orientation. So up until this point, we've really kind of drawn our molecules however we want, right? We had oxygen, hydrogen, and then we would have put it like that, right? That's kind of how we've done it so far. Now we're going to start seeing, well, what do these really look like in 3 dimensions? And water actually looks like this in 3 dimensions. Okay, when we see the molecule in real life, this is the real shape. And I'll show you how to identify that and how to start drawing it that way. Okay? But the question I want you to answer is, how many total electron domains are on the central atom for this molecule? How many total electron domains?
2.
Okay, here's 1, because it just contains a bond. This one contains a bond. This one contains a lone pair and a lone pair. So how many total domains do I have?
4.
I have 4. How many of them are bonding domains? 2 of them. And how many are non-bonding domains? 2. Okay, so we have 2 bonding domains. Oops, sorry. two bonding domains. If I ever, can I go back? Maybe. There we go. Two bonding domains and two non-bonding domains. While we're getting ready to go to this next slide, I want you to pull out the handout that I gave you that has an electronegativity scale on one side, and then on the back side it has a molecular geometry table. That's what we're going to use for this next section. Does anyone need a copy of that, or do we all have that? All right, let's try this one. What's the Lewis structure for the compound BCl3? Why don't you go ahead and draw that first, and then we're going to start applying molecular geometry. So I'm going to give you, about a minute and a half to try to draw the Lewis structure for BCl3, and then we will look at how we draw or how we determine the geometry of it. All right, do we have a Lewis structure that looks something like this? Cl, 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 and you've got lone pairs on all your chlorines.
What if I flip that?
You put chlorine in the middle?
No.
Oh, you mean you have a triangle like regular?
Yeah.
No problem. No problem. Okay, because that molecule could rotate, right? It just spins, and then it's going to look exactly like how I have it. Okay, is this what we had for our Lewis structure?
No.
Did you try to double bond?
Yes.
Okay. Here's why we want to keep it like this, okay? How many electrons does boron contribute? 3. So it's okay only having 3 bonds, right? And what does chlorine like to have? All the chlorines like to have what? 1 bond, 3 lone pairs. So let me show you this. If we had double bonded, right? It works out in terms of the number of electrons, but here's the problem. Now chlorine has a +1 charge and boron has a -1 charge. Because boron only brings 3, and here we've got 1, 2, 3, 4 around it, right? So that just put more stress on our molecule. So the best way to have that is just single bonds all around. Does that part make sense? Okay, you'll just get better with Lewis structures as you practice. I know you probably feel like, well, you said this was the rule, and now you're not following the rule. Like, I get it. But you'll start to just feel like where makes the most sense for each of them, okay? Let's look at now the molecular geometry for this structure, okay? I want you to take out your table, okay? Take out that table, and I want you to look how the table is oriented, okay? If you look at your table across the top, actually down the bottom, or down the left-hand side, it says total electron domains. So that means we are counting both bonding domains and non-bonding domains. It's total domains. Then across the top, you're looking at to say, okay, within that number of domains, how many lone pairs on the central atom do I have? We would call these non-bonding domains too, okay? You can think of them either way, but I'm usually just going to start calling them how many lone pairs do we have on the central atom? And we'll look from there. But I want you to keep this out so we know how to read this. Let's see, in this structure, on my central atom, how many total domains do I have? 1, 2, 3. So I have 3 domains. And do I have any lone pairs on my central atom? So no lone pairs. So I'm going to go to my table and I'm going to say, okay, I need 3 electron domains until it meets no lone pairs. So what shape is it?
Triangle planar.
Yep. Trigonal planar or trigonal planar. But it makes a triangle that's all in the same plane. So that means this molecule lays flat and just makes a pure triangle. The electrons are spread out as far as they could possibly be. There's nothing that's affecting it or really making it need to go up or go down. So this is called a trigonal planar molecule. Do we feel okay about how the table works? We're just finding the combination of those two things. 3 domains, no lone pairs. Yes?
Write that table on this.
Sure. I don't mind. Okay, I'm going to show you now. I'm going to pull up a image here so we can see it in 3 dimensions. Okay, this is an app that allows us to see molecules in 3 dimensions. Right now it looks exactly like it did when we drew it in 2 dimensions, right? But I have the ability to zoom, to turn the molecule. So if I turn it, now you see how it's all in one plane, right? Pretty cool, huh? So I can make it go, I can make it spin, I can look at it from every angle, so I can see right away that that it is planar, right? Everything's in the same plane. That kind of makes sense? So it lays flat. Okay, I'm going to bring this up when we do other molecules too, but I wanted you to be able to see that. Let's try the next one. Let's try CBr4. This would be called, what would the name be? Yeah, carbon tetrabromide. Very good. Carbon tetrabromide. It's covalent, so we have a prefixes that we use there. Okay, 4. Is that what you had for your Lewis structure? Very straightforward, right? Carbon gives us 4. It likes 4 bonds. Bromine is in fluorine's group, so it likes 1 bond, 3 lone pairs. It's very straightforward. Okay. Any questions about drawing the Lewis structure itself? Because in order to do molecular geometry, we have to feel good about Lewis structures. Oops, so sorry. Now tell me, how many total domains do we have here? 4. 1, 2, 3. 4 is we have any lone pairs. So we go down to 4 domains, no lone pairs. What's the shape? Tetrahedral. Now, do you see how this is different than just a... Okay, let's talk about this first. If this molecule was in 2 dimensions, what would be the angle between these two? It would be 90 degrees, right? But look at the angle which tetrahedral molecules say they are. 109.5. And that's higher than 90, right? So that means they've gone out of the plane and they've become 3-dimensional to be able to spread those electrons out even further than 90 degrees. Because if it laid flat, those electrons in the bonds could only be 90 degrees apart. But instead, they figured out a different orientation to spread themselves out as far as possible, which is 109.5. And so in 3 dimensions, it looks like this. There's a little triangle base, and then the other atom is up on the top. It kind of forms a pyramid. Okay, and we're going to look at that here on the screen as well. Okay. So here is carbon tetrabromide. Okay, you see how, can you guys see that molecule okay? You see how now it's in 3 dimensions? Right? It's got this triangle type base with my central atom, and this one is pulling it upward. So you see how these bonds are greater than 90 degrees apart? Now we're at 109.5. So I can move my molecule around, and if I spin it around, it still is exactly the same shape. Right? It still is going to have that triangle base and one on top. Okay? Do we see how that works? You guys are going to use this app tomorrow to build some molecules and to look at the geometries of them. Okay, but you see how that works? Right? It's not in the same plane. If we're going to lay these flat, we see there's a plane of them here, there's another plane of it a little bit lower, and then there's one way down here. Okay, does it help to picture them a little bit more now? Right? Okay, let's look at another one. Here we go. NH3, let's try this one. Then we're going to look at the geometry in real life with this one. We've probably already done the molecule for NH3, but we can do it again real quick. 5 plus 3, I need 8 electrons. Okay, that's what my Lewis structure looks like. for NH3. So now let's count the total domains. How many total domains do we have? 1, 2, 3, and so we have 4 domains. And how many lone pairs? How many of those are lone pairs? 1 lone pair. Okay, so we need to make sure we're not looking at 3 domains in 1 lone pair, right? We've got 4 total domains in 1 lone pair, which means I'm going to go down to 4, slide over to 1 lone pair, and it's called it's called Trigonal Pyramid. So this shape is extremely similar to tetrahedral, but instead of on top being another atom, it's the lone pair. They're still spread out 109.5 degrees. You see that? Right? They're still oriented in that way. So this would be called trigonal, not trigonal planar, but trigonal pyramid. Right? Because it forms that pyramid shape. So I'll show you that in 3 dimensions. The only thing about this app that I'm using to show them is that they don't explicitly show the lone pairs. It shows the shape of the molecule, but it doesn't show a visual of the lone pairs. So let's compare this to, we saw BCl3, or what was that, BCl3 earlier, that it was completely flat, right? This one is still all 3, so it almost looks there like it's flat, but when we shift it, we see that it's really not, right? It forms that pyramid type shape, but up here on top would be where the lone pair sits. The app itself just doesn't show the lone pair. Okay, but you see how it automatically assumes that there's a lone pair there, and it builds the shape correctly. Yeah, Pat, sorry.
Is this why there's like the 3D printed thing?
Yeah, in Chem 2, we 3D print molecules with the right angles and stuff like that. Okay, any other questions? We feel good about molecular geometry? Yeah? Okay, very good. Let's kind of speed through these next couple here. Oops, where I'm going. All right. Okay, we already talked about lone pairs. I don't need to do more notes for this. Okay. What about double bonds? How many domains do they count for? Anytime you have a multiple bond leading from the central atom out, it still only counts as 1 domain. We talked about that a little bit before. So if you've got a double bond, it still only is counted as 1 domain. Okay? So let's look at a molecule of carbon dioxide, CO2. CO2 gives us 4. So I need 16 electrons. That's what I think the Lewis structure should look like. All of our electrons are accounted for, and all of our atoms have exactly what they want, right? Carbon wants 4 bonds, oxygen wants 2 and 2. So how many total domains do I have here? 1, 2, right? Because a double bond still only counts as 1 domain. That's why when I gave you the original definition of atoms, I kind of said how many things are around the central atom. So there's 1 thing, 2 things, right? But a double bond still counts as a single domain. So if I have 2 domains, no lone pairs, what's my shape? Linear, right? There's no other way these can orient themselves except for in a straight line, right? They want to be as far apart as they can. So this is 1 domain. This is the second domain. Okay, and there's no lone pairs because there's none on carbon. We don't count lone pairs of outer atoms. Okay. So we asked the question if there's 2 central atoms. If let's say we do C2H6. Okay? What this would look like is carbon, carbon, hydrogen, 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 hydrogen. Okay? There's our H6. These molecules work out to be just bonds. Okay? Because this would be 12 plus 6 is 18. 2, 4, 6, 8, 10. Nope, I can't add. 4 times 2 is 8, plus 6 is 14 electrons. 2, 4, 6, 8, 10, 12, 14. Okay, So if I was going to look at the molecular geometry of this molecule, I look at the individual central atoms. So I'm going to say, what's the molecular geometry of this carbon? Then what's the molecular geometry of this carbon? So I identify it for both central atoms, or as many central atoms as there are. In this case, both carbons have 4 domains, no lone pairs. So it would have 2 different tetrahedral. Do you want me to show you what that would look like with the app? Okay. So what it would look like.